Okay, our next speaker is Yizhang Wang from Peking University, speaking on a two-stage parsing method for text-level discourse analysis.
Thanks for the introduction. Hi, everyone. I'm Yizhang Wang from Peking University. This is a joint work with Professor Sujian Li and Hofeng Wang. Now let's get started with our paper, two-stage parsing method for text-level discourse analysis. First, I'd like to introduce some background knowledge of our work. For text-level discourse analysis, it is the task to identify the discourse structure of text. All we can see, it analyzes how text is organized to be coherent and logical. The most famous theory about this is the rhetorical structure theory, with its abbreviation as RST. According to RST, the text, which is shown on the left, can be represented with a tree structure, as is shown on the left, on the right. Sorry. Sorry, it doesn't work. So I lose the cursor. Please, can you hear me? Yeah. Can you hear me?
Yeah. Just say something?
Yeah, because the slides doesn't work.
It's working here.
Yeah, because I want to swipe this. Yeah, it doesn't work. So.
Can you restart? Yeah. Sorry, the computer crashed. We're having a problem.
Sorry for this. Let me try it. Okay. At least let me try it with all the scripts. RST also depicts which part in a discourse parse tree is more important by tagging nucleus or satellite on each part, as is pointed out in the red box. So for this task, our goal is to parse a text into a tree with nuclearity and relation labels. To do this, several algorithms have been proposed before. Among them, the very popular one is the transition-based method. As in other typical transition systems, a stack and a queue are maintained. Then at each step, the parser either performs after, shift, or reduce action. Finally, the discourse parse tree can be derived from the sequence of shift-reduce actions. This is just the very classical transition system for building a parse tree. But the point here is that how can we get the discourse relations? Previous transition-based discourse parsing system usually employ a unified framework to parse the tree structure and get the relation labels at the same time. To do this, they combine the reduced action with 3 nuclear types and 16 relation labels. So there are totally 42 reduced actions in their system. This kind of combination guarantees that they can get the labeled parse tree using only one unified classifier. Here for the classifier, we can see that each reduced action actually has 3 parts. The first part indicates it is the reduced action. The second part is the nuclearity type. And the third part indicates the discourse relation. Even though this parsing system is very simple and intuitive, we argue that it may suffer from some problems. The biggest problem is data sparsity. because there are so many relations. Simply combining them with a reduced action could yield totally 42 actions in the unified transition system. The proportion of these actions is shown in the left figure. We can see that they are very, very unbalanced, and many of them are very scarce. So it is definitely very difficult for the classifier to distinguish among so many classes. So our proposal is that if we can remove the relation labels from the transition system, the number of actions will reduce to a great extent. The number of the 4 actions that we need to build a naked parse tree is shown in the right figure. We can see the number is reasonably larger, so the classifier can get more sufficient training. More importantly, compared with the complete discourse parse tree we can get from previous parsing systems, the naked parse tree we get through only 4 actions is already contains the whole tree structure. Another motivation is for relation labeling. Thanks to the 2-stage parsing style, we can treat the relation labeling separately and more elaborately. The intuition here is that the language usage may differ at different linguistic levels. In this table, we show the top 5 frequent discourse relations at 3 levels. So we can find that the top 5 relations for intersentential level are very different from those of the other 2 levels. Secondly, we also find that some relations tend to occur at specific levels. To give an example, this diagram shows the distribution of 4 relations over the 3 different levels. We can see that most of the condition and manner means relations are intersentential, while the other 2 are mostly interparagraph. This observation agrees with our real experience. So we propose that relation labeling should be done at 3 different levels. So here is our parsing algorithm. We divide the parsing process into 2 stages. In stage 1, our goal is to construct the naked tree, which has no relation labels. This is done using the transition-based parsing system with only 4 actions. Then in stage 2, based on the naked tree we get in stage 1, we can assign a relation label for each internal node, describing the relation between the left child and the right child. Moreover, we found that the naked parse tree we get in the first stage could help with the relation classification, even though we may concern about the error propagation from stage 1 to stage 2. Here are some details of our approach, including the features and classifiers. Since the size of our corpus is not very large, we find that some traditional machine learning algorithms currently perform better than recent deep learning framework for our task. So we manually extract some features, including the parsing status feature, n-gram features, and so on. These features are also used in previous work. The new features that we firstly use is the tree features. Thanks to the parse tree we get in the first stage, we can know the height, the depth, and of the right node, and we also know the node itself and the parent node is nucleus or not. This information are helpful for the relation labeling. After extract the features, we train 4 SVM classifiers for the 4 classification tasks. To evaluate our system, we use the most popular data set for test-level discourse parsing, the RST discourse tree bank, and we report the standard metric, the F-score. We compare our approach with 6 state-of-the-art methods. The first 2 are traditional feature-based methods. The third and the fourth are based on recently proposed neural network models. And we also compare our system with 2 transition-based systems. The results shows that our system can outperform other parsers on the span and nuclearity and ranks 2nd for the relation. Especially compared with the transition-based systems, our system gets a significant improvement on the span and nuclearity. This is mainly due to the proper design of the actions in our transition system. We also conduct further study to incrementally test how each part of our system contributes to the final improvement. Compared with the simple unified framework, we first decompose it into 2 stages. Then we add 3-level relation classification technique. And finally, we add tree features to our system. We found that the 2-stage parsing technique can improve our system for all of the 3 metrics, while 3-level relation classification and tree features also prove to be helpful for the relation classification, which is expected. Finally, let me conclude our work. First, we presented a 2-stage parsing method for discourse parsing, which separates the relation labeling from the tree construction. And then we tuned the challenging relation labeling part with 3-level relation classification and the tree features. Finally, according to our experiments, our system gets currently new state-of-the-art performance. In future work, we'd like to update the features and the classifiers with the latest models. And to further solve the data-specific problem, we would like to incorporate more data from other sources. That's all. Thanks for the attention.
We have time for questions? 1 or 2 quick questions? Okay, so let me ask a question.
Yeah.
Do you think this could be applied to other kinds of discourse representations?
Yeah, actually, we have tried that to represent the whole the discourse from using our tree structure. Right? Mm-hmm. Yeah, but we need further experiments to show the effectiveness.
Okay.
Yeah.
Okay, great. Any other questions? Okay, otherwise let's thank the speaker and